infinite also in the other direction. Obviously is an ideal body, but is interesting for us because sometimes it's possible to consider some physical cases approximated as this type of body. For example, the behavior of the ground. The ground can be considered as semi-infinite solid with the plane surface sketched here as the surface of the ground when where we walk, we live. And we have to do, as usual, some assumption. When we start an analysis, we have to list the assumption, and we consider constant thermophysical properties, no internal generation. When we have to write the equation, no internal generation inside, a uniform boundary condition on the exposed temperature. So for x equal to 0, we consider a uniform and constant in time temperature T equal to Ts. This is one possible boundary condition. When we will solve exercises, we will discover that it's possible to have other boundary conditions. So exist other solutions for different boundary conditions, for example, imposed flux on the surface. Another assumption is to consider the temperature as uniform in all the points of the body at the beginning. So we are analyzing a transient problem, so the time is a variable. We need an initial condition. For us, the initial condition is to have temperature uniform everywhere, equal to Ti. Due to the assumption listed here, we imagine to have a one-dimensional problem because we imagine to have heat transfer only in the direction normal to the surface. So for us is the x direction. Okay, it's clear for all of you? If nobody speaks, I assume another assumption that for everybody is clear. Wait, because the moment. Okay. For us, the dependent variable is temperature, that is a function of x, the unique coordinates, and time. So, considering one-dimensional case and no generation inside the transient equation, the equation to be solved is this one. The second derivative of temperature in x equal to 1 divided by the diffusivity, multiplying the first derivative in time. Partial derivative because t is a function of both x and tau. We have to couple two boundary conditions. For one-dimensional case, we need two boundary conditions and one initial condition. And the boundary conditions are for x equal to 0, for all the time, temperature is equal to Ts. So at the surface, always, except at the beginning, the temperature is imposed equal to Ts. Second boundary condition, far from the surface, so for x that tends to infinity, we consider, and for all the times tau, we consider that the temperature is equal to the undisturbed value, to the initial value Ti. Initial condition is that for all the point x, so all the x coordinates, for tau equal to 0, so at the beginning, the temperature is Ti everywhere. How to approach this problem is the first case in which we see a manner to solve a problem that is using a similarity variable. We have two independent variables, x and tau, and we want to convert this problem in a problem with a unique variable, eta, called similarity variable. So we have to combine together the two independent variables x and tau to create a single variable n, eta, called similarity variable. how to do this. We have to, okay, we start here the similarity solution. The similarity solution is, we start by defining a similarity variable eta in this way. X divided by the square ratio for diffusivity when multiplied time. We recognize inside this similarity variable the Fourier number. The Fourier number was defined before this one. The Fourier number is the diffusivity by the time by the divided by a length, a characteristic length of a phenomenon to 2. In a similar way, here we have to create a non-dimensional variable and this non-dimensional similarity variable is dimensionless, is a dimensionless variable by introducing something that contains time and space. And so the manner to create a dimensionless variable when we have time typically is Fourier number. So we create this spatial writing of a Fourier number, because similarity variable for us is not directly the Fourier number, but is 1 divided the 2 square ratio of Fourier number. And we want to assume that for us, our dependent variable, so the temperature, is only a function of this eta similarity variable. For this purpose, we define also a dimensionless temperature, because we want to use a dimensionless approach to solve this problem. A dimensionless temperature as a function of a dimensionless variable eta. So we define theta, that is our dimensionless temperature, as the ratio between T, our temperature, minus Ti, the initial temperature everywhere, divided by Ts, the temperature at the surface, minus Ti. And we want to write the equation as a function of theta, using theta as a function of eta. Okay, we have to couple at the beginning, we have to couple to the equation to be solved also the boundary initial condition. The previous written here boundary and initial condition have to be converted using the new variables. And so, for x equal to 0, what happened when for x equal to 0? For x equal to 0, we have that t is equal to ts. Okay, according to this one, for x equal to 0, t is equal to ts. But for x equal to 0, if we observe the new variable eta, also eta is equal to 0. And if t is equal to ts, look at theta. Theta is equal to 1, because if t is equal to ts, theta become equal to 1. So this is the manner to write our first boundary condition by using the new variables. The second one, for x that tends to infinity, or tau equal to 0, eta tends to infinity. Look at the definition of eta. If x tends to infinity, or also if tau is equal to 0, eta tends to infinity. Okay? What happens if x tends to infinity or tau equal to 0? We go back here. If x tends to infinity or tau equal to 0, the temperature is equal to Ti. So, by observing the definition of theta, if T is equal to Ti, theta is equal to 0. The second boundary condition written here is a sort of combination of the second boundary condition and the initial boundary condition of a previous formulation. Okay? This point, up to this point, is clear for all of you? Okay.
Yes, perhaps.
Okay, thank you.
You're welcome.
And now we have to write the equation, because we start from this problem. This is the equation to be solved. These are the boundary condition, and this is the initial condition. We have converted the boundary condition and the initial condition. But we have to write the new formulation for the equation to be solved. And we start by rewriting the temperature as a function of theta. This one, the first formulation at the left top part of this slide, is nothing else rewriting this one, the definition of theta. T is a function of theta written in this way. So I want to write the derivative of x, in particular the second derivative of x, because is inside the equation that I have to convert, and the derivative of temperature in time using the new variables. And I have that the first derivative of temperature in x is, this bracket is constant, Ts minus Ti is constant. But multiply the derivative of theta in eta by the derivative of eta in x, because theta is only a function of eta, but eta is a function of x. So if I have to write the derivative of theta in x, I have to write this product of the two derivatives. The derivative of theta in eta is a total derivative because theta is a function only of eta. The derivative of eta in x is a partial derivative because eta is a function of both x and time. Here, the derivative of eta in x can be written in this way, because if I go back to the expression of eta, the derivative of eta in x is nothing else 1 divided square ratio of 4a tau. 4 is out from the square ratio and it becomes 2. When I do the second derivative of t in x, it's similar. I do the same steps and I obtain the second derivative of theta in eta, and here at the denominator become 4. I have to do this element to 2, so I have 4 a diffusivity tau. Now I have to write the first derivative in time, and the first derivative in time is similar. I have to write again a constant Ts minus Ti, the derivative of theta, total derivative of theta in eta, and the derivative of eta in tau. The derivative of eta in tau is written here, because in this case it's not so, okay, it's not immediate as for the derivative of x, but it's simple. So eta is a function only, also of time, of tau, and its derivative in tau can be written in this way. Is nothing else a mathematical step, is a derivative, but I write it to help you to doing the calculation. So finally, what I have to substitute here is minus eta divided by 2 tau. And doing, yes, okay, this is the expression with this one, that is the derivative of eta in tau. Now I have to substitute the second derivative of temperature in x and the first derivative of temperature in tau in the Fourier equation, that is this one, the equation to be solved. And I obtain this formulation. I simplify, for example, I simplify by the bracket that is a constant Ts minus Ti. I simplify by alpha I here and here and so on, and I obtain a new equation that is this one. So for me now the problem is a problem written in terms of theta as a function of eta. This is the equation to be solved, and these are the boundary conditions to be coupled with the equation to be solved. Okay? And okay, I have obtained here, is written what I have explained to you, that okay, the transformation is successful because I have been able to write the new equation in terms of a unique similarity variable eta that contains inside x and tau. To solve this new problem, we introduce another variable. So it's important that it's absolutely clear up to this point. We have a new problem. We can imagine to start from this point. This is the equation. These are the boundary conditions. And to solve this problem, we want to introduce a new variable to simplify the calculation, the mathematical approach. And I solve this equation defining a new variable. I call y the derivative of theta in eta. For me now is y. So considering this one and going back to this equation become this one. Okay, because the second derivative of theta in eta for me is the first derivative of y in eta, and y is the derivative of theta in eta. Okay. I can separate now the variables. I can take on one side y, on the other side eta, and is simpler in this case to solve the problem because I can integrate left and right, and I obtain the logarithm of y is equal to minus 2 eta to 2 divided by 2 plus a constant. Okay, here I have written logarithm of C1 because you consider that typically I write here C1. But to simplify the calculation later, it's useful for us to write the constant as a logarithm of a constant. Is again a constant. Logarithm of C1 is again a constant value. But written in this way, when I take the exponential, it's easier because I can simply write from this formulation to this one, I take the exponential of both sides. Having here logarithm of C1, I can write here C1 multiplied by the exponential of minus eta to 2. When I arrive to this point, I introduce again the old variable. So I remember that for me, y was equal to the derivative of theta in eta. I substitute the derivative of theta in eta, and now I have this equation by integrating again. So I arrive here, I integrate again, and I obtain this formulation. Okay, C1 is the first constant to be evaluated, C2 is the second constant to be evaluated. How to obtain the value of a constant C1 and C2? I have to use the two boundary conditions that I have written before. And for eta is equal to 0, if you remember, for eta is equal to 0, theta was equal to 1. Yes. Yes.
I'm sorry, but I don't get the previous part. Can you go back to the previous page?
I go to the previous page and
I don't find, I mean, I was not able to understand the logarithmic of like why it was taken ln C1. Like it is in a constant like C1 when we integrate. So why it was taken ln C1?
Why I introduced logarithm of C1? Is
yes, because you know, yes, because when we integrate, there is a constant created, like plus
yes,
C1.
It's a constant,
so why are we taken?
A logarithm.
But why we have taken logarithmic mode?
Yes, but a logarithm of a constant is again a constant. So it's a manner to introduce a constant in a manner useful after, because I can write also constant C1 to 2, or I don't know, square ratio of C1 is always a constant. Okay, it's important that you write a constant value, not something that is dependent on my variable. So writing logarithm of C1 is similar to write C1. It's the same to write C1. Is in both cases a constant. Writing logarithm of C1 help me when I have to take the exponential. In the next step here, I take exponential. Okay, and is useful for me to have to be able to write C1 instead of exponential of C1, because it's absolutely the same. I can explain it better. It's a constant in both cases. Logarithm of C1 or C1 is a constant value. Okay. If C1 is 5, is the same to write 5 or logarithm of 5. It's in both cases a constant value. Okay, but writing logarithm of C1 when I take the exponential is easier for me. Simplify life to us when we have to go on in the solving problem. It's more clear now? A bit?
Yes, ma'am, it is clear. I get it.
Okay.
Thank you.
You are welcome. So, okay, we are here solving the, we have to obtain the constant C1 and the constant C2. And if I I use the first boundary condition for eta equal to 0, theta is equal to 1. And if eta is equal to 0, I have that this first part of the second member is equal to 0. And if theta is equal to 1, give us that C2 is equal to 1. So C2 is obtained. The second boundary condition, that is for eta that tends to infinity, theta is equal to 0. If I substitute here, I obtain, okay, theta is equal to 0. C1 is what I want to obtain. The integration from 0 to infinity. This bracket is a known function for which, if the integration goes from 0 to infinity, the values of the integration, the value of the integration is equal to square ratio of pi divided by 2. Is a known is something like cosine. Okay, it's a function known for which the integral from 0 to infinity assumes this value, square ratio of pi divided by 2. So substituting and rearranging, I obtain that C1 is equal to minus 2 divided by square ratio of pi. Finally, I have to substitute the constant in the expression of theta, and I obtain finally this solution. This one in red is our final solution. And the function, this part, the second part of the solution, that is 2 divided by square ratio of pi integration, is called error function, Gauss error function, and is called ERF. Is a function of only the variable eta, written in this way. So my solution is theta equal to 1 minus ERF of eta. Is we can define also a complementary function, ERF-C, that is defined as 1 minus ERF. So it's written here. This ERF is called error function. ERF-C is called complementary error function of the variable eta. And this is the graph, the plot of the error function as a function of a variable eta. The shape of this function is like that. And it's possible to have also tables in which you write, you can read, sorry, the ERF. So this table refers to the complementary error function. So please do not confuse ERF with RC. Our solution is theta equal to ERF-C, or 1 minus ERF. So if I use the values in the table, I obtain directly ERF-C, that is directly our theta. And for the different value of here, the variable is not called eta, is another name, is another variable, but it's the same. This is the table that refers to the function in general, complementary error function in general. And using this table, is possible to solve the problem when I have to obtain the temperature field in a semi-infinite solid. Because, okay, after all the mathematical step, remember that knowing this function and using, for example, the table, I'm able to obtain what was theta as a function of eta. So theta is nothing else, something that gives us the temperature. So our temperature as a function of the space and time in our body, that is a semi-infinite solid. So keep in mind the physical problem. So then we need to do all the mathematical step, all the calculation, but finally the final aim is to have the temperature field inside my semi-infinite solid. Okay, this is the, wait a moment, okay. This is the how to evaluate the flux. If I know by means of a solution of the RC the temperature distribution, the temperature field inside my body, I'm also able to calculate the heat flux at the surface. So the heat flux is written here for us, dot, that means watt, two apexes means for unit area. So this one is watt for unit area, watt divided square meter. I use to calculate the heat flux the Fourier law. The Fourier law without the area, because it's for unit area, this calculation. And I want to substitute, I have to calculate the first derivative of temperature in x. And I use what I obtained before, the first derivative of temperature in x as this shape, this expression, and in particular then the derivative of theta in eta now is known, because the derivative of the derivative of theta in eta is this one. And so I can obtain, I can substitute what I have calculated, I have obtained before, to obtain the final expression for the heat flux at the surface. Heat flux at the surface means that this is the general expression, sorry, for the heat flux. When I want to evaluate the heat flux at the surface, I have to calculate this expression for x equal to 0. For x equal to 0 means that eta is equal to 0, and so this exponential is equal to 1, because if x equal to 0, eta is equal to 0, and so the exponential become equal to 1, and I keep only this fraction, conductivity, temperature difference, divided the square ratio of pi a tau. Okay? Any questions? Okay. And then we have finished the chapter and we start with a new one. Okay. As I say before, it is possible to have other boundary condition for this type of problem. So same geometry, same case with a semi-infinite solid with only one direction x. But it's not necessary to have at the surface specified surface temperature. We solved the problem for this particular boundary condition, specified surface temperature, that is a Dirichlet boundary condition. But some analytical solution exist also for other type of boundary condition. In this chapter, in this course, I do not present to you the solution for the other cases, but it's interesting that you know that it's possible to have analytical solution also for example, constant its flux at the surface. So if I impose its flux at the surface, I have the analytical solution different than the solution we obtained, but another analytical solution. The second possibility is to have another boundary condition, convection at the surface. If I apply this type of boundary condition, a convective boundary condition at the surface, so for x equal to 0, I have again an analytical solution. Third possibility is to have energy pools at the surface. This last one, so the temperature that change with sign on the surface. This last boundary condition is very interesting because it is the behavior of the sun radiation on the surface of the ground. If we want to use this model for a physical problem, I say to you that it's typical the case of the surface of the ground. And which is the boundary condition at the surface if we consider the ground? Typically is the solar radiation. The solar radiation that influences the temperature at the surface. In particular, you know that the solar radiation changes during the day, because we have sun during the day and no during night, obviously. And so the temperature responds to the solar radiation in a similar way to what I write in this equation. With a period of 1 day, I have the shape of a temperature which can consider it following a sine shape. It's okay for all of you? Well?
Yes, it's okay.
Okay, so
Thanks.
I change my presentation if the computer responds to me. Okay, and the next chapter is numerical methods in heat transfer. And we have finished now the part related to conduction. And before starting convection, I want to say something about the numerical methods. So how to simplify the solution of a problem, not using an analytical solution, but a numerical approach. Up to this point, we used only analytical solution. But if you go back in your mind to the cases we analyzed, we can recognize that we considered simplified problem, simple geometries, and cases with a lot of assumption that allowed us to reduce the variable or simplify the geometry, but in some cases it's not possible to do this type of simplification because sometimes the problem is complex, the geometry is three-dimensional geometry and so on, and it's not possible to reduce the case to a very simple one. And in this type of case, it's better, is written here, it's better an approximate solution than an exact solution with two simplified models. What is the meaning of exact and approximate? The analytical solution is exact because solving the equation, you are able to find exactly the temperature field in a body for all the points of the body. But if I simplify too much the problem, okay, I have the exact solution, not of a real problem, of a simplified one. The approximate solution is the numerical one. When I use the numerical approach, I have an approximate solution in sense that I modify the differential equation and I convert the differential equation in an algebraic equation. So in this case, this is the first sense of saying approximate, because I don't solve really the differential equation, but I substitute them with algebraic equation and I solve a system of algebraic equation. The second problem when I use a numerical approach is that I do not have the solution in all the points of my body, but because of the fact I have to create a mesh in my system, in my body, I will obtain the solution only for the nodes of my mesh. And so it's in this sense that the solution is approximated. But sometimes it's better to have an approximate solution of a real problem than an accurate solution of a too simplified model. The other case in which it's useful to have a numerical model is when I have to do a parametric study. When I have to do a parametric study means that I have to solve the same problem in different cases by changing, for example, the thermal conductivity, by changing the length of my body, by changing some element. When I have to do a lot of calculation in a parametric way, frequently it's better to use the numerical approach. And what is this numerical approach? Now I show you something to clarify this point to you. Okay, for example, the first idea is this one. I consider a derivative. So, okay, I use the finite differences method. And I have to replace the derivative by differences. The idea is to replace the derivative inside the equations with differences. And what is the meaning of using differences instead of derivative? In this sketch, you have a curve, a function, f as a function of x, and I want to approximate the first derivative of the function in a point x. And look at the graph. I consider a small dx, so a small change in the dependent variable x that I call delta x, and the corresponding variation in the function is delta f. So the idea is I substitute the first derivative of f in the x with the, yes, I write that this is the limit of the delta x that tends to 0 of the ratio delta f divided by delta x. This is the correct manner to write it. And I can write directly what is delta f, that is the function is evaluated in x plus delta x minus the function evaluated in x. This is correct from a mathematical point of view. But if I imagine not to take the limit for delta x that tends to 0, but directly to take the fraction, what is the, okay, I want to approximate and take and substitute the derivative with directly the fraction. Obviously, the error in this type of approximation is bigger if bigger is the value of delta x, because more delta x is small and approach to 0, as the correct writing suggests to us, more the approximation is correct. For big delta x, the approximation is absolutely not valid or lead to relevant error. This is the basic idea. So this one is the idea of finite differences. How to obtain the same finding, the same equation written here at the top part of the slide. I can use another approach to obtain also other formulation for the first derivative and also to obtain the formulation for the second derivative. And in particular, we want to use the Taylor series expansion for the function f about the point x. So now I write expressions that are mathematical expression. Nothing to be explained except, okay, it's a mathematical, it's a manner to write the function of x, of a function f in the point x plus the x using the Taylor expansion series. And I can use this formulation if I consider x plus delta x, the function in the point x, the point before x plus delta x, the first derivative of x, plus another contribution that is 1/2 of delta x to 2, the second derivative, and so on. I have to add all the members, all the contribution in the second member that are of this shape. 1 divided the number of a contribution factorial, delta x to the number of a contribution, so again, for example, 3, and the derivative, the third derivative of the function f in x, and so on. If I want to write the expansions, the Taylor expansion series for x minus delta x, I have to put a minus when I have, for example, the first contribution, the third contribution, the 5th contribution, and so on. I have minus. Okay. Now, after writing these two Taylor expansion series, I use them by, okay, in the first case, neglecting all the terms except the first two. So I take the first one, the first expression, I neglect from this element, and all the other are neglected. I take only this part, this one, and I rearrange it to obtain an expression for the first derivative of the function f. And I obtain exactly this one. That is what I obtained before. That is this one, the same expression. Okay. I write that the first derivative can be approximated using this expression with an error that is a function of delta x. That means bigger is delta x, bigger is the error in the approximation. This approximation is called forward difference form. Why is called the forward difference form? Because I obtain an expression for the first derivative looking to a forward value of the function f, a value calculated for x plus delta x. The second expression is obtained from the second expression of the previous slide. Again, neglecting from this member to the other, from this term of the second member and also the other, and taking only the first two terms of the second member, and rearranging this expression to obtain again an expression for the first derivative. And I obtain this one that is written in a different way, because in this case I have a function evaluated in the backward point, x minus delta x. Again, the error is proportional to delta x. This is called backward difference form because it looks back, the function looks back at the previous point, x minus delta x. Now I obtain another formulation for the first derivative that is obtained by subtracting member to member. So, sorry. If I take this expression and I do this expression minus the second, I can simplify, for example, this point, and I obtain only something that is the difference between this element and this element, and rearranging again, you can try to do the calculation, the mathematical substitution, but trust me that we obtain this expression, with this third expression for the first derivative, that is called central difference form, because it uses the value of a function after the point x, so the function evaluated at the point x plus delta x, and the function evaluated in the point before, so at the point x minus delta x. Obviously, at the denominator, I need to put 2 by delta x, because the segment that I consider to approximate the derivatives is refer to a length that is in the x coordinates as length 2 delta x. The error in this case depends on delta x to 2. Up to this point is clear for all of you? You are sleeping, my dear students, or you are still with me?
Yes.
Okay.
Yes, with you, teacher.
Okay, thank you.
Sometimes sleeping.
Sometimes sleeping, okay, but sometimes it's.
We are trying our best to focus, Professor.
It's a bit boring topic, this one. The heat transfer course is a theoretical course mainly, so I know that is sometimes it's boring. Next year, with a course of energy and building, it's more interesting and more exciting. Okay, and
This one is also interesting, Professor, but the thing is, in the PDF, there are like a lot of function are simply simplified. Like, it has neglected all the factors and just simplified in one form. So it is taking time to proceed in our mind how this is got from here to there.
I can understand so much because you speak fast, too fast for me. And repeat, please.
I'm sorry.
More slowly.
No, I was just saying there are like, I'm sorry, Professor. It's like, see here, like subtracting member to member, but one can obtain these equations. So like all the parts, all the, above parts are just simplified in the one part. So it is taking time for us to, process all these procedure that has taken.
But, okay, but you are not asked to do the calculation now. I say to you, trust me that you find this final, that by subtracting member to member, you obtain finally this equation. If you want later at home, when you study, to verify that if I subtract member to member, you obtain, okay, it's good. But you are not asked to do the calculation, to do the subtraction in this moment. No, okay. And
yes, it's just basically for our understanding.
Okay, it's for our, yes, okay, it's clearly, it's easier to understand if you do the calculation. So I go more slowly, okay? And
please, thank you.
No, not a problem, absolutely. It's correct that students say to me, Professor, too fast, you have to go slowly. Not a problem, absolutely, because in a classroom, I'm more able to understand if the student follow me. Imagine that I'm in my home with a computer and I do not see your faces. And so it's impossible to me to understand if you follow me, if you are bored or not, and it's a difficult manner to teaching in this way. But otherwise, I try to go slowly. Okay, I can.
I'm sorry, I have a question.
Yes. Sorry?
In the central difference, yes, this slide. Central difference form that you wrote all delta x 2.
Okay.
Why this is that You roll.
Why? Okay, because if you do the subtracting member to member, okay, I go here. If I do this one minus this one, and you consider, okay, you have that the first member that you neglect is this one minus this one. And you will obtain 2 divided by 3 factorial delta x to 3 and the third derivative of the function f in x. This is the first term that you neglect in writing the central difference form. If you rearrange it, and when you rearrange the formulation, you divide all the member by delta x, because if you go here, when you want to obtain an approximation for the first derivative of f, you divide by delta x, okay? So the first term that you neglect is proportional to delta x to 3, that divided by delta x become delta x to 2. But this error means that the first term that you neglect, that for us is the error, the bigger error that I neglect, is proportional to delta x to 2. In the 2 previous cases, the first term that you neglect is proportional to delta x. If you use the central difference form, the first part that you neglect in the formulation is proportional to delta x to 2. The same in this case. If I sum member to member the previous 2 equations, if I do this one plus this one, the first member I neglect is the fourth derivative, so delta x to 4, but doing the fact that I have to divide by delta x to 2, I will obtain delta x to 4 divided by the delta x to 2, and finally delta x to 2 is the first part I neglect. I suggest to you, when you go back to the slide and you try to do this summing and subtracting, try and you will see that is clear. But otherwise, if will be not clear for you, you can ask me and I explain again. But trust me, if you try to do the summing and the subtracting is simple, is nothing difficult, is absolutely a simple mathematical step. Okay, so summing.
Thank you, Professor.
Nothing, you're welcome.
Teacher,
Yes.
but sometimes we use the central difference form for solving the problem, because it's I think that the central difference form, it's very precise than the backward and forward difference form.
Yes, I know. Yes, in fact, typically we use the forward difference form and the backward difference form. I know the central difference form is not used. It's only to complete the explanation that it exists also the central difference form, but it's not so used because, as you say, is imprecise. Okay, yes. In the exercises, we will not use it. So
thank you, Professor.
You're welcome. The second derivative is obtained by summing member to member the 2 equations, and the second derivative depends on the function estimated in the point x, in the point before, and the point before, sorry, x minus delta x, and the point after, x plus delta x, divided by delta x to 2. So keeping in mind the different expression for the first derivative and for the second derivative, we can starting from this type of problem, that is the steady state one-dimensional conduction. That is the easier one. This approach, by substituting the first derivative and the second derivative in this way, is an approach that can be used not only in heat transfer, but in all the fields of the physics problems, physical problem. For us, obviously, is interesting to apply this approach to heat transfer problem, and in particular to heat conduction problem. The case that we want to analyze is this one. We consider a plane wall only because considering a plane wall, we can use a one-dimensional approach in this case, and steady state heat conduction. And the axis is normal to the plane of the wall, and its axis. Yes?
Excuse me. I'm sorry to say, can we have break like for a while?
Okay, if you want a break, okay. Okay, we can start with a break now. Okay. And
yeah, because it's a mostly theoretical parts, and we have covered a lot in like past hour.
Okay.
So
Okay.
we can have a little break.
Not a problem, absolutely. So a break up to 11:30, a quarter of hour of break. Okay. See you later.
Thank you.
Bye.
Scusi, prof, posso farle una domanda che non c'entra con il corso?
Sì, scusami, ti ho risposto col microfono spento. Sì, dimmi.
Volevo sapere se lei ha mica qualche informazione sul test di ingresso di venerdì.
No, ancora no, perché allora,
lo sportello ha detto che i professori ci avrebbero dato informazioni, ma...
informazioni sull'orario, su che cosa?
Sì, sull'orario, sì, praticamente sull'orario.
Ecco, sull'orario. No, ancora no, perché dobbiamo metterci d'accordo.
Ok, quindi ancora da decidere, pensavo
No,
fosse...
dobbiamo ancora deciderci perché poi dipende dalla disponibilità dei docenti. È online, lo sapete il test.
Sì.
Sì, dobbiamo ancora organizzarci.
Ma verrà creato anche un canale Teams, immagino.
Di solito sì,
Ok.
ma vi arriva. Allora, il test lo preparo io perché abbiamo un database online su Aula Web e è una
Certo.
cosa random, nel senso che abbiamo un database di domande e random viene creato il test e quello lo confeziono io. Poi però di solito la sorveglianza al test non la faccio io e la fanno due miei colleghi, quindi sono loro che si occupano di questa parte e vi manderanno poi una mail in inglese dove ci sono tutte le istruzioni. Appena decidiamo, me lo sono scritto, ho un post-it gigante con scritto test di ammissione
Ok.
e è una cosa che devo fare.
Più che altro non ci siamo iscritti da nessuna parte, nel senso c'era scritto soltanto di chiedere allo sportello.
Dovete scrivere allo sportello chi vuole fare. Also, for a student that want to do the admission test next Friday, you have to write an email to the student office, sportello studente, ok? Sì, dovete scrivere una mail allo sportello studente così loro ci danno il numero più o meno degli studenti e noi scriviamo, viene scritta una mail agli studenti che sono interessati.
Va bene.
Ok, prof, io volevo solo chiederle anche di quant'è la durata del test.
Un'ora.
Un'ora? Quindi 2 minuti a domanda ci sono più o meno.
Sì, è un'ora.
Sono 30 domande, ok.
Sì,
Va bene, grazie.
ma è a crocette, cioè alcune domande
Sì.
Qual è l'unità di misura della conducibilità termica? Voglio
Certo.
dire, robe così, e ci sono 3 possibilità, una con, non so, ohm rispetto a... cioè, per uno che sa le cose ci mette 10 minuti a farlo, non sono cose complicate. Ci saranno 1 o 2 esempi in cui magari bisogna calcolare una portata, faccio per dire, conoscendo la velocità, la densità e la sezione, cioè proprio robe base. Ok?
Prof,
Grazie,
perché
prof.
sul sito online c'è solamente un esempio di prova. del
Sì.
2016, mi
Quelle
sembra. E l'altra volta
sono
parlando con Ilberto aveva detto che forse ne avrebbe caricato un altro, giusto per avere una migliore idea
io
insomma, degli
glielo sconsiglio.
argomenti.
Okay, we are speaking about because a student, sorry, asked me which test. You are right. We are speaking about something that is not important for the student, but in particular, at this moment, we are speaking about the admission test that is needed for all the students. And the admission test, you have to look at the page of energy engineering that refer to this point, to the admission test. You have a long page in which you have all the information about how to do this admission test, the content, and you have also an example of an admission test. To have an idea of the possible questions. No, direi che un altro test gli dico di non darvelo perché sennò abbiamo esaurito le domande nel database, perché non è che ne abbiamo 200.000 domande, sennò sapete già le domande. Quindi un esempio vi basti e vi avanzi. Il livello è quello lì, se sapete fare quello lì sapete fare tutto. Cioè, se una lato fisica tecnica e un po' di macchine e qualcosa di elettrotecnica lo passa, non è che ci siano robe pazzesche. Invece volevo chiedere, c'è quello studente che mi ha detto che è gestionale?
Adesso non è presente.
Ah, ok, ma ha fatto la triennale proprio di gestionale?
Sì.
Ma è già laureato o no?
Mi sembra che si laurea a ottobre.
Ah, ok, perché come si chiama, scusate, ma non per farmi i fatti suoi, perché sulla pagina io volevo guardare per se aveva una carriera ponte, volevo guardare la sua carriera precedente, perché io mi occupo della gestione della carriera ponte e della gestione della pagina iscrivibilità dove si analizzano tutti i dati, le informazioni. Volevo sapere come si chiama, perché per ora sulla pagina iscrivibilità non mi risulta nessuno di gestionale. Me lo dite come si chiama questo ragazzo, così mi vado a controllare.
Suprani Francesco, prof.
Suprani Francesco. Allora adesso poi mi controllo, grazie mille. No, perché per capire se è già presente, se non... Ah no, Suprani Francesco, ok. Infatti avevo messo un punto interrogativo perché non compare da nessuna parte che laurea avrà. For the student, for the foreign student, we are not speaking about something interesting for all the students. We speak Italian, sorry, because we are speaking about something related to a student, Italian student that has a particular career. So nothing interesting for all the students. When I speak Italian is only because it's not important for all of you. Trust me. Suprani Francesco, ok? Infatti non compariva in nessun modo cosa avesse fatto, cioè cosa, allora è laureando e avrà gestionale, allora me lo devo poi, devo considerare la sua carriera ponte perché mi sa che ce l'avrà. Va bene, grazie mille. Allora adesso mi faccio un po' di pausa anch'io però ragazzi, a dopo.
Prof ha sempre la condivisione dello schermo accesa per info.
Grazie mille della info, non che stessi facendo niente di segreti industriali, ma grazie della info, non credevo. Okay, we start again. Siete ragazzi?
Ci siamo.
Yes, right.
And
Okay.
switch off the microphones because otherwise, okay. So we analyze finally how to apply this approach to a neat conduction problem. And in particular, we consider a one-dimensional case. So a plane wall, for example, we consider the axis X normal to the plane wall, and the thickness of the wall is L. We consider to have each generation and constant thermal conductivity. So the equation to be solved is this one. And we want to rewrite this equation with the approach suggested before. First of all, we have to decide in which point we will solve the equation, because one of the limitations of the numerical approach is that I do not solve the problem for all the points of my field. I do not analytically solve the temperature field so I can know the temperature everywhere. But I have to decide at the beginning where my solution will be available. And to do this, I create a mesh, a so-called mesh, that is a grid of nodes in which I will have the solution. For a one-dimensional case, the mesh will be on the x-axis, and I divide to split the wall, in this case, in capital M sections of equal thickness, and the thickness of each section is delta x equal to L, that is the overall thickness of the wall, divided by the number of sections, capital M. I will obtain, capital M plus 1 nodes or nodal points from the point 0 to the point M. My solution will be for each of one of these points. And wait, because my computer, okay. I have to substitute to my derivative, second derivative, the formulation for the second derivative obtained with the finite differences. I will use as come si dice? Non apex. Pedice, footprint? No, it's not footprint. Wait, I don't find the name in English. Wait. Subscript, sorry. Subscript. And I use a subscript the name of the node that I'm considering. So this equation is written for the node M, and I will for writing the second derivative relative to for the node M, I have to consider the temperature in the node M, in the temperature on the node before M minus 1, and the node after M plus 1, divided by delta x to 2, and considering the generation for the node M that I'm considering. This equation written in this way is written for all the interior nodes. So for all the nodes from M from 1 to M minus 1. That means if I go back to the sketch, from the node 1, so from this one, to the node M minus 1. So only for the interior nodes, not for the boundary nodes. To write the equation for boundary nodes, I have to use another approach. Okay? So the approach that is writing the equation to be solved in a different way using the finite differences give us the equations only for the interior nodes. We need two additional equations because the unknown value, the node where I have to evaluate the solution, are m plus 1, not m minus 1 as the interior node. So I know I need two more equations obtained by solving an energy balance for the element at the boundary. So for the node 0 and the node m that are the node at the boundary, I use to obtain the equation to solve an energy balance for the volume associated to that nodes. The volume associated to those nodes is as thickness equal to delta x divided by 2, because the distance from the node 1 to the node 0 is delta x, but the volume that I have to refer to consider only the boundary node 0 as thickness delta x to 2, only 1/2, because the other 1/2 refers to the node 1. Then I have a sketch that, okay, here in this sketch is more simple to you to understand, but now step by step. Now it's clear that to obtain the boundary conditions, to obtain the two equations for the boundary nodes, I have to use another approach. I have to solve an energy balance for the boundaries volume. And which type of boundary condition I can consider? Specified temperature, specified flux, the usual boundary condition that I specified temperature, the boundary condition, specified flux, that is the Neumann boundary condition, then convection and thermal radiation. I think that this slide clarifies better to you how to proceed. Okay, if I have the first boundary condition, that is specified temperature boundary condition, means that for the node 0 and for the node m on the other side, I know already the temperature. So for that point, the problem is yet solved, because the final aim is to find the temperature field of my wall. In the two boundary, the problem is solved, the temperature is known. So in this case, only if I have specified temperature boundary condition, I have no need to write the energy balance for the volume associated to the boundary node. But for all the other cases, I have to write the energy balance of a volume associated to the node at the boundary. And the energy balance is written here, squared in red. And for a steady state case, remember that now I'm analyzing a steady state case with no time as an independent variable. For steady state case, the energy balance for my node can be written in this way. The summation from all sides of the heat transfer rate that arrive to my nodes, plus eventually if I have generation inside, is equal to 0. This is the basic equation to be remembered when I have to write the energy balance for my node. All contribution of heat transfer that arrive inside my node volume plus the generation equal to 0. In this case, all sides for a one-dimensional case means from left or from right. You can see here two pink arrows, one from left and one from right. First of all, we have to analyze this sketch. As previously explained, the volume associated to the node at the boundary, the node 0, is only this pink slice of my wall, okay, is this pink portion that has a thickness delta x divided by 2 that is associated to the node 0. Why? Because the remaining delta x divided by 2 is associated to the node 1. The node 1 has a portion of thickness delta x divided by 2 on the left and one portion of thickness delta x divided by 2 on the right. Each node has a volume associated to it that has a thickness delta x, 1/2 on the right and 1/2 on the left. The unique nodes that have only thickness delta x divided by 2 are the boundary nodes, because on the other side they have, for example, a fluid, a boundary condition, and so on. So we have to write the energy balance for this pink volume of thickness delta x divided by 2. Look at the arrow, pink arrow on the right. This is the contribution of the transfer rate that arrive inside my node boundary volume by conduction from the adjacent node 1. Obviously, I assume that the node 1 has a different temperature with respect to the node 0, so I have a heat transfer rate by conduction between the two nodes. One is the contribution that I have to consider, one of the contributions that I have to consider in the summation that you read here, all sides heat transfer rate. How to write the heat transfer by conduction from the adjacent node 1? By using the Fourier law. This one is the Fourier law, in which the derivative is approximated as the temperature in the adjacent node 1 minus the temperature in my node 0 divided by the distance, that is delta 0, Ka. Okay, from left. Okay, the plus, if you go here, is what I can read in the last equation of this slide. Plus what? Plus the generation. I'm analyzing a case in which I have heat generation inside. So also in the pink volume associated to my node 0, I have heat generation. And I simply write the generation that I have locally, A gen 0, but the generation also can be not uniform inside the volume, is not necessarily uniform. So locally, in that point, I have a generation E gen 0 multiplied by the volume associated to the pink zone, and this is the area multiplied by the thickness delta x divided by 2. The only unknown contribution is what I read here, Q left surface. So what arrive on my pink volume from left? This contribution depends on the type of boundary condition that I want to apply on the left surface. And can be, I can have on the boundary condition, that is the left surface of my pink volume, I can apply specified flux boundary condition. For example, I decide to have a Neumann boundary condition in which, according to which I know that on my boundary I have Q0 dot two apexes, the imposed heat flux at the node 0. So the left contribution that I have to add to the summation all sides is simply the heat flux multiplied by the area on which the heat flux is applied. This one is the first possibility. The second possibility is that I decide to have as boundary condition on the left side of my wall convection boundary condition. So the first term here, Q left surface, is expressed by means of the Newton equation, knowing the convective coefficient and knowing the fluid with which my surface exchange heat by convection. The third possibility is my surface on the left side, exchange it by thermal radiation with the surrounding. And so I introduce the Stefan-Boltzmann law. I have to know the temperature of the surrounding, I have to know the emissivity of my surface, and I can write the energy balance in this way. Or also combined convection and radiation. In this case, I introduce both the Newton law and the Stefan-Boltzmann law. Okay, is correct? Is correct? Yes, I know that is correct. Is clear for all of you up to this point? I go too fast, or you are able to follow me?
It's
okay.
It's clear. It's good.
Okay, thank you. Well, now another small step. I have to consider a particular case, the insulated boundary. So one of the possibility of a boundary condition that I can apply to the left side of my wall is to have insulation. And if I have insulation, means that this boundary is an adiabatic boundary. And that means that I can simply consider the case of the specified flux, this one, and I can consider its flux equal to 0. So I can refer to the specified flux boundary condition and impose 0 its flux. Another manner to consider this problem is to imagine to create a sort of mirror. I explain better. You know that when I have an axis of symmetry, the axis of symmetry is an adiabatic surface for us. So when you analyze a phenomenon, you recognize to have an axis of symmetry over a plane of symmetry, you immediately know, you immediately assume that on that axis or on that plane, you have adiabatic boundary condition. In this case, you do the opposite procedure. You know that the surface is adiabatic, and you imagine that surface as a mirror. You create a sort of mirror image or your real volume or your real domain, and on this mirror image you apply, you create the same nodes that you have in the actual domain. In this case, your adiabatic surface become a sort of axis of symmetry, plane of symmetry. And you can consider in this case the node 0, that for the actual case is a boundary node, in the mirrored case become an interior boundary. And obviously is not an interior boundary, an interior point, sorry, become an interior node, an interior point. And for an interior point, you can use the approach for the interior nodes. I repeat because I have saying a wrong word, and so it's not clear for you, I think. I have to create, I have an insulated boundary. That insulated boundary is an adiabatic one. I transform this adiabatic boundary in a sort of mirror. I create a mirror image equal to the actual domain. And in this case, your adiabatic surface become a plane of symmetry. And the node that was at the boundary in the actual case become an interior node in the mirrored domain. The point 0 now is for an interior node for us, and you can use the approach for the interior node. That was the previous, the first one, this one. This one was the approach of the interior node that can be applied for the node 0 in the mirrored domain. And so I can write this equation. That is exactly the same equation that I obtain if I apply directly the boundary condition of specified flux with its flux equal to 0. But you can select which procedure you prefer. Okay? Now, if for the one-dimensional case is clear for all of you, we can start analyzing the two-dimensional case. Again, steady-state conduction. So the temperature field is not a function of time, is only a function of space. And okay, the equation to be solved is this one. With a two derivative of temperature in x, temperature in y, and the generation. I consider this domain, so two axes in this case, x and y, because I have to analyze a two-dimensional case. So the node is identified by two indexes, m and n, m in the x-axis, n in the y-axis. And also in this case, I have to divide the x-axis in spaces. Here I go from the point 0 to the point M, and the y-axis from the point M to the point capital N. The spacing is delta x in the x direction. The spacing is delta y in the y direction. Finally, I obtain m+1 nodes in x with only m-1 interior nodes, and the same n+1 nodes in y with only n-1 nodes as interior nodes. Is absolutely similar, but is in the two direction. For steady state two-dimensional conduction, the equation for the interior nodes is this one. And because it's nothing else, applying the finite differences to the two derivatives. And so I obtain the derivative, the second derivative in x. In this case, subscripts are two. The first identify the position in the x direction. The second subscript identify the position in the y direction. Okay, so this is the derivative centered in the point in the node Mn that, if I consider the second derivative in x, must take into account the node in the same n, but following m, and same n and previous m. So if I consider the derivative, the x derivative, I have to consider the same n, but I have to consider this node and this node. To do the second derivative in the x direction, I have to take into account the node mn and the node m-1n and the node m+1n. The same for the derivative in y. Similar approach. And plus the generation centered in the node that we are analyzing, Mn, equal to 1. So this equation is referred to the node, generic node Mn, here sketched in this graph. I have to write one equation for each node, for each interior node. So for m that goes from 1 to m-1, and n that goes from 1 to n-1. Now, I want to define a parameter that is a geometrical parameter beta that link together the spacing in x and the spacing in y. So it's not absolutely imposed that delta x is equal to delta y, depending on the mesh. And in particular, the mesh can change in the two different directions when I have to analyze different thermal behavior in the two directions. For example, if you know that the temperature in your two-dimensional domain change a lot in the x direction and change not so much in the y direction, you will do the mesh equally spaced in the x and y direction or not? No, you will do the mesh that is thinner in the direction in which I know that the temperature field change more. Because if I have more point in the direction in which I know that the temperature change more, I will have more information about this change. In the other direction, also having a low number of points, I do not lose information because in that direction the temperature changes not so much. Is clear for all of you? So also the creation of a match depends on knowing a bit the phenomenon, depends on what I am expecting to obtain from the analysis. If I know that in the x direction the change in temperature is bigger, in that direction I insert more points in my mesh, and so that means that delta x will be smaller than delta y. It's clear? Va bene, se nessuno dice niente. If nobody say no, I assume that it is a yes. And so I can introduce a parameter beta that link together the spacing in x and in y. And wait. And define beta as the ratio delta x delta y to 2. Introducing this parameter, I can rearrange the previous equation in this way. This one is a mathematical step, nothing difficult. You can try then to substitute and rearrange, but trust me, is simple. And I obtain this equation. That is the general case with generation and with a value of beta depending on the case. If I'm interested in a particular case for which beta is equal to 1, that means delta x is equal to delta y, and I have no generation, this is a special case, but can be considered as a common case. In a lot of cases you can consider no generation and beta, irregular shape of a mesh, so beta equal to 1. In that particular case, and only in that case, the temperature, if you substitute and simplify and rearrange, you will find that the temperature in one node is the average of the temperatures of the adjacent nodes. This final equation written here means that, if I go back to the sketch, the temperature of this central node Mn is the average of the temperature here, 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 and here, the 4 adjacent nodes to the central node. Okay? And it's useful because if you are able, if is the case allow you to consider a regular shape of a mesh with beta equal to 1 and you have no generation, it's simpler to calculate the temperature in each node as the average of the temperatures of the adjacent nodes. Now, up to this point, this one was the equation for the interior nodes. Case 2-dimensional, steady state heat conduction, but for the interior node. How to proceed for the boundary nodes? And here we have again the sketch of my domain. We have the volume in gray and the volume associated to my boundary node in pink. So this pink volume is the volume associated to the boundary node to And again, for the steady state case, the equation to be considered, the reference equation to be considered is this one. The summation of all the heat transfer rate that arrive inside my pink volume associated to my boundary node, plus, if present, the generation inside the pink volume is equal to 0. In this case, we have two directions in which I have to work, the y direction and the x direction. So I have 4 contributions that arrive on my volume. The left, from right, from top, and from bottom. I have to consider all the contributions. And all the contribution. So now it's not in the slide, but will be in the numerical example that we solved, that we will solve in classroom next Wednesday. For example, from left, I have a conductive contribution from node 1. From right, so you have a conductive contribution from the node 3. From bottom, you have again a conductive contribution from node 4. And from top, in this case, for example, it's suggested to consider a convective contribution from the fluid. But how to write the different contribution will be more clear when we will do the exercises next Wednesday. Keep in mind that the equation to be considered to write the energy balance for the boundary nodes is this one. Now, another step is inserting the time. Not always I have steady state cases, but if I have to consider transient conduction cases, I have to introduce time, and I have to also to create a discretization in time. I have to define a time step, delta tau, for which evaluate the solution. So the limitation in the numerical solution is that I have the solution in space in defined point of my domain, points created according to the mesh. So the temperature field will be not known for all the points of the domain, but only for the points of my mesh. And also from the transient point of view, for the time point of view, the solution will be known only for the defined time step, not for all the possible instant in time, but only for the defined time step. And a manner to here, this sketch, I think that can confuse you because okay, is the sketch referred to a one-dimensional case in X and transient case in which I have also to change time. So is useful this sketch only to show you the how to write the time index. At the subscript, you have the space index in one-dimensional case, or index X, M and N if I have two-dimensional case. And as a superscript, you have time with the index I. Superscript I is used as index for time step. So I equal to 0 correspond to initial condition. Now, the problem is how to, which formulation use to simplify, to approximate the derivative in time. Because in the previous case, I have to approximate the second derivative in space. In both one-dimensional, two-dimensional case, I have the second derivative. And I have one possible solution. The approximation is defined. When I have to consider a transient problem, I have to approximate the first derivative of a temperature in time. And I have two possibilities. For the student that asked to me before about the central difference form, you can see that you were right. You can see that in fact we do not consider the central difference form. The unique two possibilities that that are discussed are forward and backward difference form. But we have two possibilities: forward or backward difference form for the derivative of temperature in time. If I use the forward difference form, that means that I consider the temperature in my node M at the time in the future I plus 1. If I consider the backward difference form, it means that I consider the previous value of the temperature in my node M at the time step I minus 1. Which is better? It depends on what I want to consider. And in particular, if I decide to use the forward difference form for the approximation of the first derivative in time, I generate the so-called explicit method. Explicit method is a method with positive aspect and negative aspect. The positive aspect is already in the name, is an explicit method. Explicit method that means that I will write one equation for each node, for each interior node, and for each node, this equation can be solved alone. So now I show you in the following example of equation written, but the explicit method allows us to solve the problem for each point in a separate way. In the second formulation, implicit method, using the backward difference form, means that I have to solve a system of equation, because I have to solve the equation for all the nodes all together for each time step. So from a mathematical point of view, it's a bit more complicated to solve the implicit method. One can say, okay, but if, as you explain, because of what you explain now, I select for sure the explicit method, always the explicit method. No, because sometimes I can have problem of stability. Explicit method that is easy to be implemented can create a problem of instability of the solution. So if I do not select properly the time step, and then I show you how to select it properly, I can obtain a problem of stability of a solution. On the contrary, the implicit method that is a bit more complicated to be solved, to be implemented, because I have to solve simultaneously for each time step all the equation for all the nodes. This implicit method has no problem in terms of stability, no limit on the size of time step. Is not so complicated to solve the problem of stability. That means that when I use explicit method, I have to keep in mind that I have the possibility to have instability, and I have to do an analysis, a preliminary analysis, to correctly select the time step. The time step. After this correct selection, I can go on in the solution without problem of stability. It's okay? Now,
Yes.
transient, thank you. Transient heat conduction. Transient heat conduction, here is showed the simpler case with dimensional case without generation. So the temperature is a function of x and tau. I have no generation. And I decided to use the explicit method. That means I decided to express the first derivative of the temperature in time using the forward difference form. Using the forward difference form, I obtain finally this expression. If you look at this equation, is simple to be solved because the only unknown is this one. The only unknown is in this equation is the temperature of a node of my node M. This one is the equation clearly for the node M. For the node M, the only unknown is the temperature of the node M at the time 1 plus 1, because all the other members of the equation are the temperature of the node M itself, or the temperature of the adjacent nodes M plus 1 or M minus 1, but all for the previous time step, for the time step I, that is already solved. Because when I have a transient problem, the procedure is this one. I need obviously an initial condition. Initial condition means I have the temperature at the beginning known for all the nodes of my mesh, of my domain. Then I start to solve the problem for the instant 1, for the instant I equal to 1. And based on the knowledge of the initial condition, I can solve this equation for each node. After this first solution, in all the points, the temperature at the instant 1 is known. I go to the time step 2. In the time step 2, I can solve for each node this type of equation, knowing the temperature at the instant 1. And so I go on instant by instant, time step by time step, by solving this type of equation for each node, knowing the temperature of all the adjacent nodes in the previous time step. It's very simple. Which is the problem? The problem is the selection of a time step, because remember that the explicit method can lead to problem of stability. And how to select properly this time step? I write the equation in this way by taking by explicit way the unknown variable. This one is the unique unknown variable of my equation, because the other are for known time step, the previous time step that is already known. To verify the stability, to impose the stability, to select properly the time step, I have to impose that the coefficient, this one in bracket, the coefficient of the temperature of the same node at the previous instant is bigger than 0. So this bracket must be bigger than 0. Okay, now, then I can also, okay, I go to the, not to the next slide, but the slide after, because I want to explain to you the stability criterion, because we select at the beginning to use, we decide to use the explicit method. We write the equation in this way. We solve step by step for each node, but we have the stability problem and how to solve it. So the explicit method is easy to use, but is not unconditionally stable. I have to impose limitation on the time step to be sure to have a stable solution. And I write each equation for each node in a similar way as written here, as this one for each node. And that means the temperature in the instant I plus 1 equal to a function of the temperature of the adjacent nodes at the previous instant I, but the first term of the second member must be the temperature of the same node in the previous instant I. The coefficient, all the coefficient of all the temperature of the nodes in the previous instant, so all the AM for m that goes from 0 to m, that means for all the nodes, must be bigger than 0. This one is the stability criterion. This coefficient, all the AM coefficient contain inside the formulation also the Fourier number, for example, and the Fourier number is a function of time. So imposing that this bracket, for example, is bigger than 0, impose to me to select the time step properly to avoid the stability problems. Okay, Fourier number, I forgot to say to you, but it's written here that I define a mesh Fourier number, delta Fourier, again as diffusivity by time by characteristic length to 2. Characteristic length for us is delta x, time for us is delta tau. Okay? And also for a boundary condition, so one equation for each interior node, and also the two equations for the boundary nodes. So in this system of equation for which the coefficient is bigger than 0, I include also the equations for the boundary nodes, for the node, for example, 0, and for the node m at the boundary. Typically, the equation for the boundary condition lead to different limiting value of the AM coefficient, and I have to select the time step delta tau that satisfy all the AM bigger than 0. Here, the second possible choice is the implicit finite difference formulation. That means I decide to use the backward difference form for the first derivative of temperature in time. And in this sense, I can use two different manners to write this equation. That is this one, sorry, this one or this one is absolutely the same. Someone understands better if I write in this way, someone understands better if I write in this way, but it's the same. Observe this one. In this equation, the only known value of a temperature is this one, because it's the temperature at the previous instant I minus 1. At the present instant I have 1, 2, and 3 unknown. If I look at this one, it's the same. I use only a different notation, but in this equation, again, the only known is this one, that is the temperature at the instant I. In the forward instant I plus 1, I have 1, 2 and 3 unknown value. Having a free unknown value of temperature for each equation means that I can solve each equation in a separate way, but I have to solve a system of equation. I have to write an equation, a system with all the n+1 equations for the n+1 nodes of my domain, and I have to solve step by step the system of equation all together. It's clear this point? So from the point of view of mathematical solution is a bit complicated because I have to solve a system of equation instead of one equation for each node as I do for the explicit model. But in this case, I have no problem of stability. Okay, I go back to the if I have a transient one-dimensional heat conduction, this one is the explicit method. Sorry, it's better to wait. Otherwise, it's not clear. And the first, this equation refers to the explicit approach, for which you remember the stability criterion imposed for all the nodes, the coefficient of the temperature of a node in the previous instant bigger than 0. So that means that this bracket must be bigger than 0. That means that delta Fourier must be less than 1/2, less than 0.5. So if I have already defined the mesh means defined the delta x. The delta x is defined. This limiting value on the delta Fourier means a limiting value in the time step. The time step must be selected to have a Fourier number less than 0.5. The implicit method, on the contrary, is unconditionally stable. No problem in the selection of the time step delta tau. Wait, okay. Now, the last two slides, so you have to resist a few minutes. This explanation is a sort of physical, to give you a physical sense of the limitation in the delta Fourier in the time step. Because, okay, now we know that for the stability criterion, all the coefficients must be bigger than 0. That leads to limitation in the Fourier number, that leads to limitation in the delta tau. Okay, it's okay, we will do this, we will do that, but why? From this physical point of view, here is a small physical example that gives a sense to this limitation and the stability of the solution. And in particular, consider this case. It's a case based on the second law of thermodynamics. I have to consider this case at the instant I, so at the beginning, I have this situation. I have 3 nodes, central node M, and 2 adjacent nodes, M-1, M+1. The central node has a temperature bigger than the 2 adjacent nodes, bigger of the value epsilon, bigger than 0, is not important. So a bit bigger than the others. I can write here that the temperature in the node M-1 at the initial instant I is equal to the temperature of a central node M at the same initial instant I minus epsilon. The same for the node, the adjacent node on the other side, M+1. One can write to consider, to solve this problem is a one-dimensional case, transient. I want to know how the temperature field change in time. So how the temperature field can evolve in time. And I want to apply the transient one-dimensional solution. You know that for transient one-dimensional with conduction problem, for the interior nodes, I can write this equation, okay? So this equation that comes from this one, from this one. So this equation, that is finally the equation that I use, comes from nothing else. This one, that is a different manner to write the Fourier equation, that is this one. Transient one-dimensional case. And so the equation for the interior nodes, and I can consider this as interior nodes, is this one. So this equation is valid also for the node M, that is my central node. So the node M at the instant after I plus 1 depends on the temperature of the node M itself at the previous instant I, and the temperature and the two adjacent nodes at the previous instant. But this temperature and this temperature are linked to the temperature at the center. And so I can rewrite this equation in a different way by substituting simply these two expressions for the adjacent nodes. And I obtain, instead of this bracket, I have this one. Okay? Rearranging, because now I can simplify something. For example, this one is equal to this one. Okay, this one minus, this one plus, and I can simplify. Rearranging this equation, I can obtain this expression. And that say to me that the temperature in the central node M at the instant I plus 1 is a function of a temperature of a central node at the beginning minus this expression. But according to from the physical point of view, according to the second law of thermodynamics, what I expect in the evolution of a temperature, I expect that the system tends to the thermal equilibrium. So I expect that the temperature of the central node decrease a bit, and the temperature of the two lateral nodes increase a bit, because they tend to uniform temperature at the final situation after enough time. And this is what I write here. But for the second law of thermodynamics, the temperature at the instant at the central node at the instant I plus 1 must be bigger than the temperature of the two lateral nodes, because I do not expect that the temperature of a central node becomes smaller than the temperature that the two adjacent nodes at the beginning, from the physical point of view. So I can write that this temperature is bigger than this one and this one. That, according to this first equation, is equal to Tmi minus 2. That means that if I couple this limiting value to this one, remembering that I can write Tmi plus 1 as Tmi minus T minus 2 delta Fourier per epsilon, I can write that this expression here must be bigger than Tmi minus epsilon. It's not so simple to understand. It's clear or not? Mi seguite? Are you ok? Siete svenuti tutti?
I'm sorry,
could you explain again?
Explain the second law of thermodynamics.
Okay.
I'm sorry.
Okay, if you observe this system, how do you expect from this that the temperature of a central node decrease a bit, and then the temperature of the two lateral nodes increase a bit? Because the final situation must be thermal equilibrium, must be temperature always in all the points the same. So, from a physical point of view, the temperature in the following instant I+1 cannot be smaller than the temperature of the two adjacent points at the beginning, because the temperature at the adjacent point increase a bit and this temperature decrease a bit, but not to go down to be smaller than the temperature of the two adjacent nodes. It's impossible from the physical point of view, from the practical point of view, according to the second law of thermodynamics, because I can't find a different manner to explain it. It's a physical sense of a transfer. So the temperature, this one, must be bigger than the temperature at the beginning of the two adjacent nodes. And the expression for the temperature in the node M and the instant I+1 is this one. I substitute in this this formulation, and I obtain from this a limit, because I neglect TMI because it's both members, and I can obtain from this a limitation in the Fourier, because I have epsilon is bigger than 0, and I can simplify also epsilon. I can change, okay, I can change the sign, here I put plus here, and I convert not bigger but smaller. This is a mathematical step, nothing complicated. And from this, simplifying by epsilon that is bigger than 0, I can find the same limitation in the Fourier number that was imposed without explanation here. This example is nothing else to give you a sense, a physical sense of this imposed limitation here given directly without explanation. Okay.
Yes, Professor, thank you.
You are welcome. And last slide for today, boundary nodes. You remember that, we have obtained how to solve the problem for because this expression and also, this expression for the implicit method were for interior nodes, because both come from this expression, that is the expression for the interior nodes. We have to write, as usual in this approach, the energy balances for the boundary nodes. The nodes located at the boundary need an equation, because I want to obtain the temperature also for the boundary nodes. And so I need an equation also for the boundary nodes, but I can't obtain it with a previous approach. I have to write and solve an energy balance for the volume associated to the node on the boundary. If I have the transient problem, you remember that without time, if I consider a steady state problem, I have only the left side. The left side of this equation equal to 0, because I was in a steady state case. When I have a transient case, means that I have temperature that depends on time, I have to add to the energy balance also the right side, that is the energy content variation in time of my volume. This expression on the right is the variation in time of the energy content of a volume associated to the node of the boundary. Because you recognize density by the volume, that is the mass, specific capacity, temperature which change with time. This temperature that change with time also for the equation of the nodes on the boundary can be written using the forward or the backward difference form. So also for the nodes of the boundary, I can use an explicit approach or an implicit approach. Obviously, if I select an explicit approach for the interior node, I have to select an explicit approach also for the nodes of the boundary. The same for the implicit. If I apply an implicit approach for the node, for the interior nodes, also an implicit approach for the boundary nodes. This is how to write the equation in an implicit method. In this equation, I consider all the contribution at the previous instant I, and I have only one unknown for the forward instant here in the derivative of a temperature in time. So as for the interior node, I can solve directly this equation only for this unique unknown in a separate way with respect to the other nodes. Also, for this equation in the explicit method, I have to find the stability, I have to fulfill the stability criterion. So also for this equation, I have to find a limitation for the delta tau. And comparing the limitation of the delta tau obtained for the nodes on the boundary with the limitation of the delta tau for the interior nodes, I have to apply the more limiting value for the delta tau itself. If I decide to use the implicit approach, I can write the equation in this way. In this case, all the members are considered at the forward instant I plus 1, and the only known value is this one. For this reason, I have more than one unknown, and I have to introduce this equation together with the other equation in the system to be solved simultaneously, step by step, to find the solution of all the nodes step by step. Finish. It's clear for all of you?
Yes, Professor.
Okay, so have a good lunch. See you on Wednesday, hopefully in a classroom, but I think so, because it's a question of weather for